very quick summary of local area networks, and then we move on to the Internet Protocol. How the Internet works. We're not going to cover LANs in detail. We are going to skip over that. You've covered some aspects of wireless local area networks in your assignment, and in next semester in computer network architectures and protocols, you'll cover many details. What I've done is just taken 3 or 4 slides from last year just to give us a summary. So I'm going to show you some slides that are not in the order that you have in front of you. We know, in fact, this first slide is from one of our first lectures, or the content is similar. We can distinguish between wide area networks and local area networks, where wide area networks are networks that connect across cities, between cities, and across the world, so between countries, for example. So over a large geographical area, normally wide area networks, because they're quite expensive, they are built and maintained by an organisation that then rents or leases access to individual users. The example that we've used before is that between our 2 campuses, from this campus to the Rangsit campus, we don't own the cables between the 2 campuses. Another organisation, we pay someone like TOT to rent access to their cables between our 2 campuses to connect between our campus and Rangsit. So with wide area networks, the network is normally owned and operated by a telecom company or an internet service provider, and then rented to end users or other companies. Local area networks connect inside your home, inside an office building, across a campus, and normally are used to connect end user devices together. That is, connect our laptops, PCs, mobile phones to communicate across a local area, a small area. Normally, LANs are owned and operated by the person who owns and operates the devices. Many of you may have your own LAN at home. You may have a switch or an ADSL router which has an inbuilt switch, and you may have a LAN cable, or maybe you use wireless LAN. So you have your own LAN at home. Okay? You own and operate the network. You set it up. You buy the cables. You own the end user devices. So usually a LAN is owned and operated by the organisation that uses the network. Okay? They have different requirements, LANs and wide area networks, and hence lead to different technologies have been developed for them. Wide area networks need to carry traffic from many users at the same time. Local area networks usually have dedicated cables for individual users. For example, this PC in the lecture room, and each lecture room has a PC and there's a LAN cable, a wired LAN cable in it. This connects, and that cable is dedicated for the communications from this PC. And then it's connected into other devices, and then that joins them together. So the point is that there have been different technologies developed for LANs and wide area networks. And within each of them, also, there are different technologies for the different types of wide area network technologies: wireless, wired, cable, coaxial cable, optical fibre, copper. And there are different types of local area network technologies: wireless LAN, different variations of wireless LAN, wired networks, wired LAN, sometimes called Ethernet, and there are many other LAN technologies. We're not going to cover how they work. We just want to say that there are different technologies for LANs and WANs. And most of the technologies for LANs and wide area networks are related to the physical layer and the data link layer. One common standard that covers many LAN technologies is the IEEE 802 architecture. IEEE creates many standards. They create this set of 802 standards, which includes wireless LAN. You studied that in the assignment, 802.11. It includes wired LAN or Ethernet, which is 802.3. And there are others. 802.5 is an old technology, token ring. Bluetooth falls in there, WiMAX, and there are others for different local area network technologies. You choose the best one which suits your needs. Mostly focusing on the physical layer and the medium access control or the data link layer. I think you've seen at least, or you've seen 802.11 in your assignment. I hope you did. An example configuration of a LAN, a typical wired LAN, which we refer to commonly as Ethernet. So the cable you plug into your laptop or into that desktop computer, we use Ethernet or wired LANs. A typical configuration is shown here. The end user devices, PCs, printers, servers, are connected via cables into some special device, a LAN switch or an Ethernet switch. For example, in this building, let's say all the computers in the lecture rooms have cables going to a switch, and in this building the switch is downstairs on the 3rd floor. So this cable from the PC actually goes into the socket on the wall here, goes through the cavities in the walls down to the 3rd floor, and there's a cable going into a special device, a switch. And other PCs in other rooms, the same. In the other building on this campus, of course, there are some office computers. They also connect into a switch, in this case a different switch. There's other lecture rooms, labs. There are some servers, our email server, our web server, database server for keeping track of students and so on. All those end user devices in this example are connected into separate switches. And then the switches are connected together. So this forms our one large local area network, all using the same technology, Ethernet or wired LANs. So switched, this star topology is quite common in most networks today, where each device connects into one switch. That switch has many cables coming into it, and the switches may connect together to join larger sets of devices together. This would be we could refer to this as a local area network here. Of course, sometimes we want to communicate internally on the LAN. I want to access some information on a database server. But often we want to communicate externally as well. Not just to other people inside the LAN, but to people outside our LAN. And that's what's shown here. There's some special device that connects us to the rest of the world, the internet in this case. We're going to look at how the internet works. That's all we want to say about LANs, except addresses. Okay. The last thing we want to say about LANs is something you've probably seen in the assignment, and you may see in some examples in the rest of this course and in subsequent courses, is what does a Ethernet LAN frame look like? In your assignment, you should have drawn a picture that looks like similar to this. When you had web browsing with Wireshark, you saw different packets. What do we see? You may have had a HTTP request, and that was put inside a TCP packet. So you would have drawn the TCP header, and that was inside an IP datagram. So you drew the IP header, and that was inside, well, in your case, it's most likely inside a wireless LAN frame or possibly an Ethernet frame. It depends on what Wireshark reported. or captured. For Ethernet, we would draw this. This is the Ethernet header. In fact, in Ethernet or wired LANs, it also has a trailer. So we draw that at the end. This is our frame. And the structure of that frame is shown in this diagram. It's just shown in a different orientation than what we've drawn on the board. That is what is inside the Ethernet header and the Ethernet trailer. Different fields are inside, and this diagram shows those fields. Let's focus on where it shows the frame here. The first two, preamble, start of frame delimiter, we normally consider part of the physical layer. Okay? And if you looked and captured with Wireshark, you would not see them. They are processed inside the hardware, and Wireshark would not capture any information about those. You probably see the next fields though, the destination address, source address, and length or type. We'd say they are fields in the Ethernet header. Sometimes in my examples I draw them like this: the source address, destination, and the type. And at the end, then we have data that's here. And then at the end we have some trailer. What is the trailer? In Ethernet, it's a frame check sequence. It's used for error detection. That is, with this information, the receiver can check, are there any errors in the data inside the frame? And if there are, ask for a retransmission. So the Ethernet trailer is simply the frame check sequence, or generally for error detection. That's the typical structure of an Ethernet frame, where the data is this portion. The standard maximum size of the data is 1,500 bytes. There are some extensions to make it larger, but the typical size we'll see is 1,500 bytes. And then the header and trailer, how big are they? It's shown here. Destination address is 6 octets. How big is that? 8. 8 something. 8 what? Octets. Octets. O-C-T-E-T-S. How big is an octet? 8 bits. It's the same size as a byte in our course. Okay, it's just the different. And at least in our case, we assume every byte is 8 bits. An octet is 8 bits. So 6 octets means the destination address is 6 bytes in length. 6 bytes is 48 bits. So the source, I will not write it, is 6 bytes. Destination 6 bytes. The type is here 2 bytes or 2 octets. 2 for the type. The type indicates what's inside of this frame. In this example, what is inside our Ethernet frame? On the example on the board, what is inside the frame? What's the data? If you had to give the data a name, what would it be? What type of data is inside my Ethernet frame? This is the header. What's inside? What can you give this a name or payload? Which protocol? Inside. IP. That is the next one inside. Okay. So what's from Ethernet's perspective, the data, this is carrying an IP datagram. The IP datagram is carrying a TCP packet. The TCP packet is carrying a HTTP request. So we look at what's inside the other one. The type field in the Ethernet header says what type of data is it carrying. In this example, IP. In other examples, it could be different values. And it uses a number to indicate. So it doesn't give the letters IP, there's a number that corresponds to the Internet protocol. Source address is the computer that sends the frame. Destination address is where it's sending to. Error detection at the end. They're the main things that we'll see in an Ethernet frame. What about the addresses? Yep. Okay. The data, normally the data has to be a fixed length in bits. So if the data I have is not a fixed length, usually an integer multiple, say of, in this case I think of bytes. So if I have 3 bits of data, I need to pad it out to 8 bits to make 1 byte. That's the idea of padding. If we have a fraction of bytes of data to send, I need to expand it out to an integer multiple of bytes. So we add some padding at the end just to fill it up. Okay, we think of that as part of the data. It's not always needed. In some cases, it's not included. The maximum size of the data is 1,500 bytes. If I have 100 bytes, it will be 100 bytes of data. But if I have 1,600 bytes, I would have to split it into 2 frames because the maximum size is 1,500. Okay. When you looked at your Wireshark capture, although the header was different, you would see some of these characteristics, I think, especially if you capture a wired LAN. Type indicates what's inside. The trailer is used for error detection. Then there's a source and destination address. What are they? They are 6-byte values, 48-bit value addresses. We've seen the structure of those addresses in an earlier topic. We've given examples. They follow this standard created by IEEE. They're a 48-bit address. Many devices use these. We refer to them as MAC addresses or hardware addresses. 48 bits in length, 6 bytes. The address is split into 2 parts. First, let's give you an example of an address. On my laptop, on my wireless LAN interface, the configuration, here's an example of my hardware address, this 48-bit address, 0026-5E, 8E, E4, 95. Except this is in hexadecimal. We need to convert it to binary, and we'd get, with 12 hexadecimal digits, we'd get 48 bits binary. So it's just an easier way to represent, instead of writing down 48 zeros and ones, we write down 12 hexadecimal values. That is my hardware address. It's the IEEE, for example, when I send a frame, that's the source address. When I receive a frame, it's the destination address. Has anyone else showed up on the list? Is anyone else on the list who hasn't spoken to me? People who need to choose their option. That's okay. We'll catch them elsewhere. Those that haven't chosen their IT option for their next semester, they need to choose. Let's write down our hardware address. That's the hardware address of my wireless LAN interface for my laptop. That, you can convert that to 48 bits. I will not try. 1 hexadecimal digit maps to 4 bits. Okay. It has some structure. The structure is the first 6 hexadecimal digits, so if we split here, the first 6 represent the manufacturer of the device. The company that made the device, the wireless LAN chip in this case. The last 6 hexadecimal digits represent as one of those devices manufactured by that company. Here we have 6 hexadecimal digits in general, or 24 bits. So we have 48 bits address. First 24 bits identify the manufacturer, and the last 24 bits identify that device created by the manufacturer. How it works is that the organisation IEEE assigns 24-bit values to different manufacturers. So a company that's going to create wireless LAN chips, they go to IEEE and ask for a 24-bit identifier, and then when they create each wireless LAN chip, they use the same first 24 bits, or first 6 hexadecimal digits, and for each separate chip, they use a different last 6 digits, so that each device gets a unique value. Remember, this is hexadecimal, 6 digits. In binary, it's 24 digits. And the idea is that all devices that use this address format will have globally unique addresses. My device will have a different address than your device, and a different address to every other device in the world. So long as the manufacturer addresses are unique, and so long as the manufacturer assigns unique addresses to all the devices they make, it will work. Except nowadays you can change the address in software. So in practice they may not be globally unique, but the aim is that they are. And the last example, where are we? IEEE, the organisation that assigns this first 6 digits, has a website where you can look up, given the first 6 digits, who manufactured that device. They have a database. On this website, what we can do is enter in the first 6 digits and it will tell us who manufactured the device. What is mine? 26. 26 5E. And we do a search, enter, and it tells me who manufactured my wireless LAN chip inside my laptop, on high precision. Okay? They're a large company that creates different network devices and other computer devices. So you can look up, given your MAC address, take the first 6 digits in hexadecimal, you can look up on this website and find out who's the actual manufacturer there. Sometimes there may be it may not be clear, but often you'll see a company that you recognise. Who manufactured the chip in this case, the wireless LAN chip? Any questions on LAN or hardware addresses? Look on your tablet, on your phone, and somewhere in the details there you'll find your hardware address, and you can find out who manufactured that device, the chip that is. Same on your laptop. In Windows you can click on the properties and see the details. We just introduced them because we'll see many examples of them. In fact, you've already seen them in your assignment. Our main topic for today is how the internet works, for today and tomorrow. What is the internet, and how does the internet protocol work, and if we have time at the end, the structure of IP addresses, not hardware addresses, but the IP addresses. First, we'll look at why we need generally internet working and internet. The problem that we have, if you think about across the world, there are many different organisations and many different technologies they can choose to build their LAN or to build a wide area network. So SIT chooses one technology for their LAN, Another university who built their LAN 30 years ago may choose a different technology, depending upon their requirements. And you at home may use a different technology. Across the world, everyone may use many different technologies to build their own LAN or wide area network. Now, with your Apple Mac, can your Wi-Fi communicate with someone's phone using their Bluetooth? So you use your Wi-Fi link and you create a direct connection and they use their Bluetooth link.
No, Wi-Fi and Wi-Fi.
Wi-Fi to Wi-Fi, yes. Wi-Fi to Bluetooth, no. You need to use the same technology to be able to directly communicate. Okay. Now we have a problem if in my network I'm using one technology and another network is using a different technology, they cannot communicate with each other. Okay. And if there are networks across the world using different technologies, how do we enable them to communicate with each other, even though they do use different technologies? And that's where we get Internetworking and the Internet Protocol. We've seen this before. We have different types of technologies for LANs and wide area networks. The aim, I want to allow any computer, no matter what LAN or wide area network technology it uses, to communicate with any other computer. Whether one uses Wi-Fi and one uses Bluetooth, I would like them to be able to talk to each other. And that's what Internetworking tries to do. It involves connecting together many different LANs and WANs to get so that they can communicate with each other. Even if they use different technologies, we let them, the computers on those networks, to talk to each other. That's Internetworking. Let's explain it with an example and give you some terminology as we go. Here's an example which has different local area networks and wide area networks. Instead of me drawing the details of each network, I'll just draw a cloud. What does that mean? Or what does a cloud represent? In the assignment, one of the questions was to draw the network topology, the typical network topology. You have a laptop with wireless LAN. What's the network topology? What does the laptop communicate with in wireless LAN? Did everyone attempt the assignment? I saw people draw some pictures. What does your laptop communicate with in Wi-Fi, wireless LAN? A router, a wireless router, sometimes called an access point. One of these things up on the wall. A wireless router, a wireless access point. They have different names via the wireless link. And then that wireless router connects via a cable onto some other device. And there may be multiple laptops in here. And you may even have a cable from your PC to that wireless router. Okay? And this may connect onto some other network. Instead of me drawing these computers, the wireless router, I will just draw a cloud to represent one local area network. That's what these clouds represent. Whether it's wireless LAN inside here, whether it's wired LAN, Bluetooth, whatever. The cloud means it's some network, some local area network. Same with a wide area network. It could be an ADSL link, it could be a multiple optical fiber links, but it's some network that connects these strange devices together. Okay? So in this case we have 6 LANs and 3 wide area networks. And there are some devices connecting them together. These devices are routers. The name we'll give them is router. A router connects 2 or more LANs or wide area networks together. So we see here's one LAN, LAN 4, and the router connects it with WAN 3. So this router is connected to 2 networks. If we look back at the details here, the details may be like this, where this is an access point, a wireless access point. Your laptop connects, the PC connects, there's a cable that goes into another device, a ADSL router, modem, which is also a router in this case. And that connects via some ADSL link to your internet service provider that also has a router somewhere in their office or in their telephone exchange. And then that connects to other routers. So this may be our cloud for Wide Area Network 3, and this is our cloud for LAN 4 as an example. This router connects 2 different networks together, one LAN with one Wide Area Network. And note it uses different technologies. Here's our wired Ethernet, here's ADSL. Different technologies connected together. This router here connects 3 networks together. Typically a router connects 2 or more networks together. Okay? Routers are packet switches. So in the concept that we know about of switching, we had 3 approaches: circuit switching, virtual circuit packet switching, and datagram packet switching. Routers use packet switching, and specifically in the internet use datagram packet switching. Okay? One of those 3. So these are packet switches. We send a packet to this one, it sends to the next one, and then to the destination. We're going to go through this terminology still using our example here. So we have local area networks and wide area networks. Routers connect them together. We'll refer to these component network, these LANs and WANs, as subnets, subnetworks. So generally we can say this is one subnetwork. This is another subnetwork. We have 9 subnets in this example, and together we have one large network. Remember, a network, we connect multiple devices together. Here we have multiple, in this case 9 subnets, connect them all together via routers, and we get one large network. What do we call that large network? What a mesh, that's the way we may connect it. Give us a more useful name. Multiple subnets, connect them together via routers, and we get an internet or an internetwork, but the short name is an internet. So we have multiple subnets connected together via routers to give us an internetwork, or we know it as an internet in short. This is an internet here, an example internet. We have 9 subnets connected together via routers to form one internet. And that's what we get today in what we use for our communications, the internet we refer to it as. It's a network that connects many subnets together via routers. And of course, in the internet, we have hundreds of thousands of subnets all across the world, all connected together via routers to form the internet. Sometimes we differentiate between a general internet, some we may use in an example or in some separate network, and the internet that we use every day, where the internet we have an uppercase I. A general internet, the concept, a lowercase I. This is an example of an internet, lowercase I. When you access Facebook, you're using the internet, uppercase I. the internet is a internet, but it's also got the name the internet. So it's confusing, I know, but the same word, but often we can distinguish between, in general, an internet and a specific internet called the internet. The next two terms we've seen and defined before. We're using datagram packet switching in the internet. That is, the routers are datagram packet switches, which take packets and send them on to the next router until they reach the destination. We separate the two phases of one problem is finding the path from source to destination as routing, and the second task is forwarding the data from source to destination, forwarding. So we say there are two tasks involved. One is finding the route, the next one is sending the data across that route, routing and forwarding. We've defined them before. In the internet, a router is a packet switch, specifically a datagram packet switch. There are also circuit switches, which we've mentioned before. And to add some confusion, in Ethernet wired LANs, we also have switches. We may have a switch inside here. In fact, this device is also a switch. It can be a router, a switch, an access point all at once. They're all functions built into the one device. But the important point is a router is a datagram packet switch in the internet. And from now on, we'll use the term router instead of referring to individual switches. So in summary, the internet is made up of multiple subnets connected together via routers. Routers are datagram packet switches, and in the internet they use one specific protocol called the Internet Protocol. Okay? We need to go through how the Internet Protocol works for how to deliver data through the internet. Before we start looking at how IP works, any question on the terminology? Make sure you're clear on what a router is. What a subnet is. What an internet is. Yep. ADSL, asymmetric digital subscriber line. It's what you use or commonly use for home internet. It is some protocol or technology that works across your telephone line for internet access. ADSL. Some people may have it at home if they have internet access.
What is inside the WAN?
So, as an example, let's say you have a ADSL router at home, and it plugs into the telephone line at home, and that telephone line goes into some telephone exchange. Inside that telephone exchange is another router, and they're connected together. That's part of the Internet Service Provider's network. We'd refer to that link, or we could call this link, a wide area network. So instead of me drawing this line and saying it's ADSL, in generally I just draw a cloud to say it's some wide area network. Maybe it's across 5 kilometres or so, but in the examples here, it could be any technology or any of many technologies. It could be ADSL, it could be a wireless link, it could be optical fibre. We don't care from the perspective of internetworking. It's some technology. Internetworking is about making it possible to communicate between any computer on any of these networks and any other, irrespective of what technologies are used inside the LANs and wide area networks. Whether it's ADSL or something else, we still need to be able to communicate via that network. And so we use Datagram packet switching, i.e. routers, and we'll use the internet protocol to send data through that network. Is that clear now?
Yes.
Just explaining to her? Okay, good. Is that clear for you? Okay. So if we have a quiz tomorrow, you'll be able to answer questions. Be clear on the terms for routers, subnets, internet, routing and forwarding. Okay. The others, all right, are important, but they are the main ones.
Internet
Internetwork is just the long term for internet. Okay, all right. We normally use internet. Internetworking is the process of sending data across an internet. Okay. So we do that by connecting subnets together. So internetworking is a procedure or process, and internet is a network. This is an internet. The process for connecting these subnets together we call internetworking. Okay? We internetwork the different subnets. For this to work, for internetworking to work, we use a protocol. We need a protocol. Okay? This is internetworking is the concept. We need a protocol to implement it. What would such a protocol need to do? Some of the requirements are listed here. The main thing, an internetworking protocol needs to deal with the differences in the individual subnets. Because our internet is made up of different technologies in the subnets, how do we cope with those differences? That's the role of the internetworking protocol. Some of those differences, in one subnet I may use my 48-bit IEEE addresses, in a different subnet I use a different addressing scheme, 16-bit addresses. So across the world, in all the different LANs and wide area networks, they may have different addressing schemes, different maximum packet sizes. We saw Ethernet has 1,500 bytes. Other protocols have different maximum sizes. How do we deal with that? Some LANs have error recovery. For example, ARQ, stop and wait ARQ, go back N. One network may use stop and wait, another may use go back N. Another may not use any error recovery. Okay? The different technologies may use different mechanisms for error recovery. In the internet, we need to cope with that. So an internet working protocol needs to somehow cope with the fact that some networks will retransmit, others will not. So there are differences amongst the way that we have error recovery, security, routing across the many different technologies. An internetworking protocol needs to be able to send data from any computer using any technology to any other computer using a different technology. How does it do that? Well, there are different approaches. So there are, in fact, different internetworking protocols. There is one specific internetworking protocol that we use every day. It's called the Internet Protocol. Okay? So we see this internet word come up very often, so it's confusing. An internetworking protocol is a general protocol. There are different specific implementations. One of them is the Internet Protocol. And that's what we use every day to access the internet. It's what all of your computers have implemented inside them. Your phone even has the Internet Protocol, some software that implements it inside its operating system. And that's what we're going to try and explain in this topic, how IP works. It turns out that IP meets some of these requirements. It can deal with some of these issues, but not all of them. It leaves some of the issues to other protocols in the internet. TCP is one that we'll come across. ICMP is another. So remember, in the internet we have this 5-layer stack. Actually, it's here. In the internet we have our 5-layer stack. The internet protocol is the protocol we use for internetworking. But in fact there are other protocols that we need as well in most cases. TCP we use on a regular basis. ICMP is used for error reporting. If anyone has ever done a ping, you ping another computer and it tells you how long a delay between your computer and that other one. That normally uses a protocol called ICMP, ping. And there are routing protocols. The important point is that the internet protocol, IP, is the center part of our 5-layer stack. Center in that it's the middle layer, but more importantly, it's the core part, it's the required part in our internet attached computers. If you don't have IP in your computer, you cannot connect to the internet. It's part of the network layer, and we're going to spend today and tomorrow and even sometime next week going through how it works.
What is ICMP? What does it stand for?
ICMP, Internet Control Message Protocol, I think. Internet Control Messaging Protocol. It's for error reporting, to find out if there's something wrong in the network.
How about ARP?
Address Resolution Protocol.
What the task?
The task of ARP is, given an IP address, find the hardware address. If you know someone's IP address, you need to know their hardware address to send them a MAC frame, and that's the role of ARP. Don't ask me about the others. These are examples of different wide area network and LAN technologies. We will cover TCP in the next topic, and then we'll finish with HTTP. But you've studied a little bit about HTTP in the assignment, and you use it every day. So whether you're using web browsing, email, voice calls over the internet, all of them make use of IP. Most use TCP, but not all, but all of them use IP. That's why it's a core part of the internet. In fact, there have been different versions of IP. The version that we're going to focus on is IP version 4. There's a new version available, IP version 6, IPv6. It's available, it works, it's used in some networks, but not in widespread use. So we're focusing on IP version 4, the old one, but the more commonly used protocol. In another course, you'll see IPv6, I think next semester with Dr. Comwit on computer network architectures and protocols. And there are other internet working protocols. Most of them are either old and did not become as popular as IP, like IPX, X25, or some that have been used in very specific networks. When they don't need IP or cannot use IP, they use some other protocol. But in most networks we see today, IP is used. In most existing networks, IP version 4, and probably many new networks, IPv6 is also supported. I would think all computers that you have support both IP version 4 and IPv6. It's just that you use just one of them, IP version 4. IP was developed by the US Department of Defense, but now is maintained by the Internet Engineering Task Force, IETF. They maintain it as a standard. Internet Engineering Task Force. It's an alternative to IEEE as an organisation that develops standards. IEEE creates standards, so does the IETF. What does IP do? And in fact, we'll see it's better to describe what IP does by looking what it does not do. We'll see in a moment. It uses datagram packet switching. Okay, we know how datagram packet switching works. We simply send a packet to the first switch, which sends it to the next switch until it gets to the destination. There's no concept of setting up a connection. with datagram packet switching. And same with IP, we do not set up a connection. So in fact, we often call it connectionless. There is no connection set up. And it operates at the network layer. It provides data delivery. That is, the goal is to deliver data from one source computer to a destination computer. IP specifies how we format our addresses. And today we'll finish with some examples, some quick examples on IP addresses. You've seen them, IP addresses. We'll try and explain how they are structured. And it has some other mechanisms. One of them is fragmentation and reassembly, and we may see an example of that tomorrow or next week. It doesn't have connections. There's no concept in IP of setting up a connection. We just send the data. It doesn't have error control. We send the data, we hope that it gets to the destination. If it doesn't, that's not a problem for IP. So there's no retransmission scheme. If we send our data and if it doesn't get to the destination, too bad from IP's perspective. Some other protocol has to deal with that. So there's no error control, there's no stop and wait ARQ, no go back N in IP. Similar, there's no flow control. We don't care if we overflow the receiver with IP. We just send as fast as we can, or as fast as we want. In that sense, it's very simple, because adding flow control, error control, setting up connections adds complexity to the protocol. IP doesn't include them. Some or many applications need such features. TCP, turns out, implements most of these features. TCP does have connection control, error control, and flow control. That's the focus of our next topic. IP does not perform any status reporting. Sometimes in a network, I want to know if a device is working. Is this web server working? Is this router working? So some error reporting or get some status of other devices. IP does not do that for us. There's another protocol, ICMP, that can do that for us. Sometimes I would like my data to get to the destination faster than your data. For example, I pay more, therefore I should get higher priority, or my data belongs to video traffic, yours is just some web browsing, so it may make sense to give priority to the video so it gets there first. IP does not do that. IP does not provide any priority. It treats every packet the same. There are other mechanisms to provide priority. IP doesn't have any built-in security. We send our data packet, there's no encryption. If you want some security, you need to use something else like IPsec, an extension of IP. The point here is that IP doesn't do all these things. It's very simple. And that's one of its advantages compared to the others, and one of the reasons why it become the most popular. Because it's simple, it's easy to implement and easy to scale to very large networks. So it works when we have millions and billions of computers using it. It still works. Remember datagram packet switching. Source sends a packet to the first switch, sends it onto the next switch, and so on. We call that a datagram. Instead of a packet, we often call it a datagram. We send a datagram to the first switch, to the next switch, and so on. What does an IP datagram look like? This is the structure of an IP datagram. Previously, we've drawn packets like this on the board, where I would say this red part is the IP datagram. As with most of our protocols, it consists of a header and some data. So our IP datagram has a header and some data. The diagram on the screen shows us the structure of the header. It shows the fields inside this header. And then the data. Let's go through some, or the most important fields. They are described on the next slide, but we'll just use this diagram. So in the header, we need to carry different pieces of information, and they are all listed here. The way we read this diagram is we read it row by row, left to right. So the first field in the IP header is the version field. It indicates which version of IP are we using. IP version 4 in our case. If we're using IP version 6, it will be a different value inside here. And then the next field and the next field, and then we come to the next row and so on. What this diagram shows is that we have 32 bits in each row, from 0 to 31. 32 bits, 4 bytes. Each row represents 4 bytes of information. The mandatory size of the header has 5 rows, that is 20 bytes of information. That is from here to here. So the typical size of an IP header is 20 bytes in length. We have the header followed by data. It turns out in IP we can have optional header fields. We always have 20 bytes, but we could have optionally other header fields. We will not go through those options. Let's just assume that there are no options in use. So we have 20 bytes of header and then data. What's inside the header? There's a version, the version of the protocol we're using, the length of the header, because if we have options, the header length increases. So it's 20 bytes plus the options. The receiver, when it receives a datagram, needs to know where does the header finish and where does the data start. And so we include a value in the header length field to indicate how long is the header. Diff, serve, ECN, used for very special purposes. Let's not describe them to keep things simple. Total length is the header size plus the data. Okay. So if the header is 20 bytes and the data is 10 bytes, the total length would indicate there's 30 bytes in this datagram. The maximum size of the total length is 65,656 bytes. So that's from the start to finish. So that minus the header gives us the maximum size of data. ID or identification is like a sequence number. We can include a number in there when I send the first datagram, number 1, the next one, number 2, and so on. Flags and fragment offset are used for a special feature in IP called fragmentation and reassembly. And when we come to that, we'll explain these header fields. Protocol, we'll come back to time to live. Protocol indicates what's inside. The same way with the type for our Ethernet frame told us inside this Ethernet frame is IP. The protocol field says inside this IP datagram is, in this case, TCP. So the protocol field tells us what type of data do we have. Is it TCP data, UDP data, or some other type? And each type has different numbers associated with them. So it simply indicates what's inside here. Header checksum is to use for error detection across the header. The receiver receives a datagram. It uses this checksum to detect, are there any errors in the header? Maybe there's a bit error somewhere in the header. It can detect them. But importantly, it doesn't apply across the data. If there's an error in the data because of the transmission, the receiver will not be able to detect that. Only in the header. So it's not so useful for data error correction, detection. And then we have a source address, the IP address of the computer that sends the datagram or creates the datagram. And the destination address is the address of the computer that's the final destination, who we're sending it to. What do we miss? Time to live. Time to live is like our hop counter in flooding. Remember our hop counter? The source computer sets the value, for example, to 3. Sends it to the first router. The first router reduces it to 2. Sends it to the next router, reduces the time to live to 1. Sends it to the next router, reduces it to 0. Now, once the time to live is 0, we have 0 time to live, that datagram is discarded. It's not sent anymore. So the time to live is used to limit how many routers that datagram is sent via. It can be used for different purposes. One is to make sure that a datagram will not be sent around the internet forever. If there's some loop in the network because of some misconfiguration, that is, send the datagram from router A to B, and then router B makes a mistake and sends it back to A. So A sends it to B, B sends back to A. If they keep doing that, they do it forever. But if we have a time to live, eventually it will reach 0 and one of them will stop sending. So that's one reason for a time to live. But think of it as our hop counter. It counts the number of hops, the number of routers that that network will traverse. Version, length of the header, total length, some sequence number, some hop counter. The protocol identifies what's the data, and importantly, the address of the computer that creates the datagram, the original source, and the address of the computer that's the final destination. So if we send from my computer to the Facebook web server, my computer's IP address would be the source, the Facebook's web server would be the destination. In the last 10 minutes, we'll just give some examples of IP addresses. Tomorrow we'll come back to how IP works, but just to finish today, something a bit lighter. What are IP addresses and how are they structured? Any questions on the header structure? You don't have to remember all these fields. For example, in the exam it would be given. Total length is the length of the datagram. Header plus data. Okay? Header length is the length of the header because we have options. The amount of data may change. I may send 100 bytes, you may send 1,000 bytes, whatever you choose.
And why total length is just 16 to 31?
So how we read this is 16 to 31 bits. Our datagram is just bits, a sequence of bits. But we view it as the first 4 bits indicate the version, the next 4 bits the header length, then the 16th bit to the 31st bit, or actually to the 32nd because we start at 0, these 16 bits indicate the total length. So the value in these 16 bits is the total length of that datagram. The next 16 bits is the ID. Then we have 3 bits of header, fragment offset, and so on. So, for example, our source address is 32 bits in length, from 0 to 31. This diagram just tries to present all of those fields in some easy to look at way. An IP datagram is just a sequence of bits, but the bits have some meaning, where the first bits mean the version, these bits mean the total length, and so on.
How do you know the size of the header?
The source computer creates this datagram, must have 20 bytes. If they have some options, they may add them, and that they will know the size of the header because they add the options. There are different options available. We will not cover what they are, but if I add an option with an extra 4 bytes, then the size would be 20 plus 4, 24 bytes. The source computer does that.
So it will be given. It will be given.
It will be given by who?
By computer.
Yes, the computer that creates the datagram would choose, do I need options? If no, then the header length is 20 bytes. If yes, depending upon the length of the options, the header length may be larger. It's up to your computer that creates the datagram. Your operating system will do it.
So what if you not include the option? And what is the total length of?
Total length, Although the ways to represent the values, think of the header length is here to here. By default it's 20, but it can be larger. The total length is from here to here. Header length plus data, where the data may be variable. If the header length was 30 bytes and the data was 50 bytes, the total length would be 80 bytes. Header plus data. That's the meaning of those values.
But in this case, it doesn't add the option.
If there were no options, you wouldn't add them. The options are part of the header. So if there were 4 bytes of options, the header would be 24 bytes. And if then there were 10 bytes of data, it would be 24 plus 10, which would be 34 bytes total length. Any final questions on the header? Again, you don't need to remember that structure. It's just to show what key information is included. We'll see some examples of those header fields used as we go through how IP works. Note, source address, how long? How long is a source address? 32 bits. Starts at 0, finishes at 31, so it's 4 bytes long. So an IP address is 32 bits in length, every IP address. This was the example before for my wireless LAN interface. I found my hardware address. I also have an IP address. In this software it calls it an internet, an INET address. When my computer creates an IP datagram, that would be the source address. What does it mean? Let's write it down and then explain the meaning of this address. In my example, my IP address is 10.10.99.251. That's the IP address of my computer. My wireless LAN interface has that IP address. You've seen these IP addresses before, I'm sure, both in the assignment and elsewhere. But we said an IP address is 32 bits. This is not 32 bits. This is in fact 4 decimal numbers. This is just a convenient way to write a 32-bit value. A real IP address is always 32 bits in length. But writing down 32 bits, remembering 32 bits is hard. So what we do is we often convert that 32-bit value to this other form, which is called the dotted decimal notation. It's a notation where we have 4 decimal numbers separated by dots. Let's just go through how do we convert from one to another. Our IP address is 32 bits. What we do is we divide it into 4 chunks of 8 bits. Okay? 4 chunks of 8 bits. So each of those 8-bit numbers we convert to a decimal number. So imagine there are 4 8-bit numbers in binary. We convert each to a decimal number. So we end up with 4 decimal numbers. And then we just join them by dots. And we get our dotted decimal notation. Let's go backwards. Let's convert this dotted decimal notation into a binary value. So what this IP address in dotted decimal notation shows us, 10 in decimal, and we convert that to a binary 8-bit value. It must be an 8-bit value because we must have 8 plus 8 plus 8 plus 8, 32 bits. What's 10 in binary? 10 decimal in binary. Anyone? You can use your big calculator, you can use your brain, you can use a piece of paper. Again, 10 in binary. except, remember it must be an 8-bit value. So 4 zeros at the front. Because an IP address is 32 bits, where we split it into 4 8-bit chunks. Each chunk maps to a decimal number. So going back, 10 in decimal is equal to 00001010. And then convert the next number. And it's 10 again, so we'll get the same 8 bits. Convert 99 to an 8-bit number. And 251. Okay. You can use your calculator, whatever you want, but the important point is that we have a decimal number, it maps to a 8-bit binary number. And now remove the dots. There's our 32-bit IP address. So this is the real IP address that your computer uses. But when us humans look at it, instead of remembering these 32 bits, it's easier to remember and write down in dotted decimal notation. That's all. But your computer always uses this 32-bit value. It doesn't use the dotted decimal notation except for presentation to the human. To convert back, split the 32 bits into 8-bit chunks, convert to a decimal, join by dots. You can do that?
Yes.
Okay, so that's easy. So remember, IP address, 32 bits, but we often see it in dotted decimal notation. On my example, there's some other IP addresses, 10.10.103.255, 255, 255, 248, 0. Let's write down the last one. Quickly convert. 255 convert to an 8-bit value is in fact 8 ones. And again, 255 is another 8 ones. 248 I've calculated before. It's 5 ones followed by 3 zeros is 248. And 0 is simply 8 zeros. One more. There's 8 there. Another IP address. Okay. The first one is the IP address given to my computer. It identifies my computer. When I send a packet, my computer puts in the source address this 32-bit value. The second one is a special one. In fact, my computer's 32-bit IP address has 2 parts. One part identifies the subnet my computer is on, and the second part identifies my computer inside that subnet. Remember, our internet is made up of subnets. Our computers are on one of many subnets. An IP address is split into 2 parts. It identifies the subnet inside the internet and the host within that subnet, or the computer within that subnet. What the second address here does is tells us which bits in my IP address identify the subnet and which bits identify my computer. The way to determine, whenever we have a 1 here, it means the corresponding bit here identifies my subnet. So this is a subnet, and up to 5 bits here. This sequence of 21 bits identifies my subnet in the internet. If you're on a different subnet, you should have a different sequence. How did I know it was those 21 bits? Because we have 21 ones in this special address here. The last 11 bits, where we have 11 zeros here, identify my computer inside a subnet. So in fact, IP addresses have two parts. They identify the subnet we're on and the computer inside that subnet. The idea is that everyone on the same subnet as my computer will have the same subnet portion here, the same sequence of bits, but we'll have a different 11 bits at the end. If your laptop connects to the same network as mine, you'll check and you'll see that the first 21 bits are the same as my IP address. And the second laptop, the first 21 bits will be also the same as what's on the board. But the last 11 bits for those three laptops will be different because they're different computers. Okay. Now if you go and connect not to SIT's subnet but connect to True's network via your 3G or some other network, you should have a different subnet address because you're on a different subnet in the internet. So for each subnet in the internet we have some address, and then for each computer inside that subnet we have some address. This is important, the way that addresses are structured, because it allows us to have billions of devices in the internet and scale well when we do routing and forwarding in the internet. What we'll do tomorrow is go back and see how IP works, and then we'll return to some more examples of the structure of IP addresses. So for now, what do you know? The internet is made up of subnets. Subnets are connected together via routers. Routers use datagram packet switching. We've seen the structure of the IP datagram briefly, and some quick examples on IP addresses. An IP address is 32 bits in length, but for us humans, we often convert it and view it in a dotted decimal notation. And the last thing, the 32-bit IP address actually has two parts, the subnet part and the computer part of the address. The subnet part of the address identifies the subnet inside the internet. The computer part identifies the computer inside that subnet. So we have some hierarchical addressing. Tomorrow we'll continue with some more examples of addressing and how IP works. And we'll see on the slides the definition of those IP addresses.